Hello everyone, my name is Akhil Kankula and I'm here along with my partner Sanjay Vardarajan. So we are here to present our project Geospatial Machine Learning Platform for wildfire risk assessment and crop health monitoring. Uh, First, let me focus on ultimate business problem that we chose. So we embarked this project on dual threat problems. One is wildfires and one more is crop failures, which is the current environmental issue that we are facing right now in the real world. So to put this in perspective, so one side utilities and emergency managers are flying blind. So they desperately need accurate risk maps to prioritize where to clear vegetation and how to do all these things. And also on the other side, farmers and governments need to know what is happening in their fields, how to harvest and all these scenarios. So our solution, the project that we are going to develop is something an AI-driven platform that transforms raw, messy satellite data into clear and operational insights. And coming to the data, here are the data resources that we chose. So to make the predictions a little bit more accurate, we just chose these data sets. So like we were not just looking at one thing, so we are combining multiple layers of information and data. So first thing is the visuals. So we are using satellite Sentinel-2 satellite imagery to give the optical data and all. So second thing is we use the heat data. So we use the NASA firms and Moody's data, which allows us to detect the active fire points in the real near time. And third thing is the context. So it's not enough to see the fire, so we need to know what is burning. So we use the USDA cropland data layer to identify specific crop types. And finally the environment. So fire behave differently, depends on the terrain. So we import elevation data, SRTM, to see the slopes and topological things. Yeah, and here comes the folder structure of the data sources that we downloaded. So in the previous class, we discussed the sources that we used for the downloading of data. So after downloading the data that we needed, this is how the data sources, data sets looks like in the local folders. So the approximate size of this is around 128 gigabytes. And coming to the methodology and the project life cycle, how we worked on this thing. So this is the diagram of the life cycle that we used for development of the project. So I just walk you through the entire life cycle, moving clockwise from the top. So first thing is data acquisition. So we started by ingesting complex raw data, specifically VIRS for fire points and SMAP for soil moisture. Crucially, we didn't download these files manually. We implemented an automated acquisition pipeline using a .NET RC file configuration. This can be done in using Git Bash. So this allowed our system to securely authenticate with NASA's Earth data servers programmatically, enabling us to continuously scrape and update our 120 gigabytes of dataset without any human intervention. And second is data preparation. So this is where we solved our hardest engineering problem. So as you can see on the right side, we dealt with massive 82 gigabytes of RAM error by developing a technique called dynamic point centering chipping to process data in manageable chunks. So we divided the data into a lot of different chunks. So we also had to fix orbit gaps, missing days in the satellite records. So by using some linear interpolation to create a continuous timeline for our models. And third step is the modeling part. So we deployed two different architectures. One is custom unit, which is used for visual fire segmentation, and LSTM networks for forecasting drought based on historical soil moisture. And fourth thing is evaluation. So we rigorously tested these models accuracy and all. So our first unit model, uh, for instance, achieved 100% validation IOU on the unseen date using our blind tests, ensuring it generalizes well to the new fires. And finally, the deployment. So this on the left you could see the end results. So this not just a coded notebook, it's a full stack web application that will be seen in the later slides. So we built a fast API backend using this model, and the Next.js as front end that renders these insights into a like 3D global real-time website. So that's how we developed the entire project.
Hello everyone, myself Sanjay. I will be discussing about our modeling approach for this project. Now let's look under the hood of the technical workflow. that powers our platform. So here we divided our modeling approach into three parts, that is data pre-processing, training and inference. First, let's look at the data pre-processing. First, we ingest the raw thermal and soil thermal data into our pipeline, and the critical step here is we apply sinusoidal projection to our data, and this fixes the geometric distortions which are common in global satellite maps. Then we execute dynamic point center chipping to extract manageable 224 by 224 pixel images. And then finally, we use linear interpolation to fill in temporal orbit gaps, which ensures that the AI doesn't get confused by missing days in the satellite record. Then let's go to the training group. Here we split the data into 80% which is used for training, and the 20% will be used for validation. We defined our hyperparameters very carefully, where we selected a learning rate of 1 to the power of minus 4 and batch size of 16 to balance memory usage with convergence speed. This is where we initialize our two distinct architecture, which is custom unit, which is used for file segmentation, and the LSTM for sequential crop memory. Crucially, we use different class functions for each stacks. That is, BC with logics is for binary classification of file pixels, whereas mean squared error is used for numerical prediction for crop health. Third, let's look at inference. Here we prepare our PyTorch data loaders with shuffling to ensure the model doesn't memorize the order of data. And then during the training group, we calculate specific metrics like intersection over union to measure segmentation accuracy and correlation for our forecasting accuracy. And then to prevent the model from overfitting, we just memorize the training data and we implement early stopping. After training, our models are saved to a file in a .pth form, which is what we actually deploy to our web application. Now let's discuss about the core architecture that we use for our model, which is UNet. As you see on the screen, our platform needs to handle complex multimodal satellite data. To do this, for a wildfires, we employ unit which acts as a spatial autoencoder. Here is how it works in our project. The encoding, which is compression, the model takes the high resolution thermal input, which is like noisy images you see on the left, and compresses it. This forces the AI to ignore the noise and capture only the essential context which is needed for our project. And then the decoding happens, which is reconstruction. That is, it expands that compressed information back out to the original sites. But this time, instead of recreating the noisy image, it generates a clean, precise segmentation mask. This is the blueprint for our wide drive model, that is UNet. Its unique U-shapes allow it to balance context with precision. On the left, we see the encoder, in which the model compresses the input image. It sacrifices a resolution to understand the context and figuring out what is in the image. On the right, we can see the decoder. It expands the image back out to figure out where the fire is. The critical component in this image is that these gray arrows that you see in the picture are the secret sauce. They act as bridges, copying high resolution details from the beginning and directly to the end. This allows us to recover the sharp edges of a fire that are usually lost during compression, giving us a highly precise output map. Now, to understand how we evaluate our unit model, we have to look beyond simple accuracy numbers and look at the actual pixels. This slide shows exactly how we grade the model's visual performance. If you look at the legend, you can see three key metrics we track in segmentation task, that is dark red, pink and green. So let's discuss about dark red. That is, this represents success. It means the model predicted fire and there actually was a fire. If any risk assessment model, our goal is to maximize this area. For pink is false negative. These are the misses. That is, the fire was there, but the model didn't see it. In wildfire management, this is the most dangerous type of error and one we work hardest to minimize. The last is green, which is false positive. These are false alarms where the model thought there was fire, but it was clear ground. So while our first model looked at space where the fire is, our second model looks at time. This is the long short-term memory network, which is LSTM, which we use it specifically for crop health monitoring. The reason we use this architecture is simple because crops don't fail overnight. A drought is a slow moving disaster. The problem with standard AI is standard neural networks treat every data point as an isolated event. They don't remember what happened yesterday. So that we use LSTM as a solution in which the text on the slide explains that the LSTM works by preserving a memory of past conditions. Now, if you look at the diagram, you see a complex system of gates, which is represented by these yellow and orange boxes. Conceptually, think of this like a conveyor belt. The monitor takes in a sequence of historical soil moisture data as it moves through time. These gates decide what information is important enough to keep and what can be forgotten. The result is here by learning these long-term temporal dependencies, the model can look at the soil moisture history from last month to accurately predict a crop stress event that might happen next week. So to power this platform, we rely on a constellation of satellite data sources. We don't just look at one thing, we rely on multiple data sets to get the full picture. First, our visuals. We use Sentinel-2 imagery. This provides us with high resolution multispectral data which serves as our primary input for seeing the ground. Second is our ground truth, which is to train the data, we need to know that what was actually burned. For this, we use the Moody's burn area product data. Third, real-time detection. For immediate awareness, we ingest NASA films data. This gives us active file points for Moody's and VIRS sensors in near real time, which is critical for future engineering. Fourth is agriculture. Since we are monitoring crops, we use a USDA cropland data layer. This 30-meter annual map tells us exactly which crop is growing in every pixel, acting as a mask so we don't predict fires in the middle of a city or a lake. Finally, environmental context. Fires behave differently depending on the terrain and weather. We import SRTM DEM data to calculate slope and aspect and ERFI weather reanalysis data to track temperature, humidity and wind, all of which are essential for calculating the risk. So why UNET and LSTM? So we didn't just pick UNET and LSTM at random, we chose them by systematically rejecting the industry standards that fail to meet our specific needs. First, we rejected standard classifiers like ResNet, that is, they only provide a label which is fire or no fire. We needed a precise map, not just a label. Second, we rejected object detection models like YOLO, which only offer us bounding boxes which are too coarse. Fires have jagged and organic shapes that a square box simply cannot capture accurately. Third, we rejected traditional ML models like random forest because these models treat every pixel as an isolated island, losing the critical spatial context of the surrounding area. Finally, for crops, we rejected statistical models like ARIMA because nature isn't linear. Soil moisture follows complex patterns that simple linear models fail to capture, whereas a LSTM network can learn these nonlinear histories easily.
Now let's focus on challenges that we have faced during the project development. So this project was not just about training the models, it's something like engineering battle. So we just faced four types of critical failures. First thing is geometric mismatch. Satellite data comes in different shapes. So trying to map VIRS sinusoidal data onto standard grids is something difficult one. So this is one of the biggest challenge we faced. Second thing is the memory crashes. So our initial attempt to process the global data caused almost 82 GB RAM requirement, so which crashed our system. Third thing is the data complexity. So we had to mine complex nested data layers from scientific HDFI files that standard tools couldn't read. And fourth thing is the temporal gaps. So satellites don't see everything every day, so we had to deal with naturally occurring 1 to 2 day gaps in our time series data. So these crashes forced us to abandon our original plan, and we have changed our plans iteratively. And finally, coming to the project promise. So this platform is not just like a prototype; it is built to grow. So first thing, we can see on the scalability. So by deploying our pipeline on distributed cloud system like AWS Lambda or Google Search Engine, so we can move beyond local testing to the real-time processing of petabyte scales global datasets. So right now, what all things are done is happened in the local, so we can move that to the AWS Lambda services. And the second thing is the precision. So we plan to extend the platform to use the harmonized Landsat Sentinel to satellite data. This evolves our current regional forecasts into hyperlocal precision agriculture insights, allowing us to monitor health down to the individual field at 10 meter of resolution. And the ultimate goal of this project is to empower environmental analysts and governments to stop reacting to disasters and start simulating them. So by predicting crop yields and harvest failures months in advance, we can secure food systems before a crisis ever begins. This is the ultimate promise that we are planning to do. And so these are the few of the references that we chose for this project. And other than this, we have a lot of different sources of data which we couldn't add in the references slides, but these are the main references which focus on UNET, LSTM, and all these things. That's it. Thank you, everyone. Hello, all. This is the web platform that we have developed using Next.js as the front end and Python fast API as backend. So the models which we created earlier, so I just integrated that with the backend Python, and I connected that Python backend with the Next.js front end to display the results. So this is how the platform real-time platform works. So for example, we just choose only California state for this project. So this works only for California state for now. So let me try with the historic data. For example, let me choose past years of 2008, and if I click on run risk prediction, so these are the data points, different parts of California. So this indicates green color of texture. That means these areas are low risk areas. That is in the year of 2008. So these areas which comes under California were very low risk areas. And let me try with the current year data. For example, 2024 or 2025. So I'm going to 2025. So if we click on run risk prediction, and if we move to the map here, so we could see two types of dots, few are in orange color and few are in red color. So that represent that orange are moderate risky, and the red color indicates high risk areas or extreme risk areas. So these are the results that the model which we developed predicted the results of the future. And let me try with the upcoming years. For example, let's say that 2030, 2030, and let me click on risk prediction. So if we see, so we could see like except one or two remaining, all regions are indicated as extreme risk areas, which indicates there's maximum uh, probability of getting involved in wildfires. And we could also see the crop stress values. This indicates how the crops are going to be in those areas for upcoming years. So this is how the platform works. So this indicates the globe, which indicates the three states. So for example, state California, Washington, and Oregon, but we just choose only California state for this project. So and whenever we click on the year and when we click on prediction, then we could see the visual representation of all these um, wildfires and crop stress values on the global graph here, which indicates the clear accuracy. And this can be scaled up to the higher quantity or large level using cloud services and all. So that's how we developed the project. Thank you.